Hello and welcome pre-AP Physics to our very first content lecture. I came dressed for the occasion. I hope you are too. So without further ado, let's begin. If you look at your notes sheet that's attached to the Google Classroom post and it's linked in this video, you should see that our topic for the day is simple harmonic motion. So I know the unit I said was waves, but actually there's this tiny little bit of content, simple harmonic motion, that'll help connect the physics stuff that we were doing to waves, which are all a little bit different. So this is kind of a go-between in the starting of the waves unit. So you might be asking, well, what is simple harmonic motion? Let's watch a video first that I think you might find interesting to see an example of simple harmonic motion in the works. So here it is. You may have seen something like this before. This video was actually shown to me by Joe Cano, so shout out to Joe Cano. The balls are pulled back. There they go. They're swinging back and forth. Notice that the shape ball that the balls are taking is actually changing. We started off in a line, it got snaky, now it's just going crazy. And actually what you should notice over time is that the shapes are kind of repetitive. And you might think of, you might be wondering, like, well, why is the shape changing? What's going on here? Actually, it might be clear, it might not be, but the balls individually, the pendulums individually, are actually swinging at different rates. So some are moving faster back and forth than others are. That's why the shapes are changing that way. Back to a little bit of chaos. We should actually end up back in the snake and then eventually swinging back and forth once again. I think it's coming up. Yep, there's our snake. And we're back. Yeah, there's the end. So the balls were moving differently. We're actually going to learn this unit how what's going on here. We're going to be able to explain why the balls are moving at different speeds, why the shape's changing, and all that. So if you'll pay attention, turn your attention to the note sheet, you've got the first definition to write down is just what is simple harmonic motion. So simple harmonic motion, abbreviated SHM for short, is motion that's consistent and repetitive. As we saw, pendulums exhibit simple harmonic motion. They move back and forth like this one on the slide. Move back and forth. It's repetitive. It's consistent. It's the same motion, just back and forth. And another example of that is the spring example that you should be seeing right here in the slide. It's going back and forth, back and forth. It's repetitive. It's consistent. So what you see here in the spring one is that it's on the ground, moving back and forth like this. But there's actually another good example of springs. They do it horizontally, like across the ground, and actually vertically as well, where you've got like a spring attached to a ceiling of some sort, and the mass can bounce up and down like this. So you've got horizontal and vertical. We'll look at some examples of that later. You'll see a good example. So that's simple harmonic motion. We need to be able to describe what simple harmonic motion, the motions are, and a really important word for that one is oscillation. So oscillation is one full back and forth motion for simple harmonic motion. One back and forth. So if it's a pendulum, you pull it back, you let it go, it swings forth, and then it swings back, and that's one oscillation. One. That's an oscillation. So our next word is period. Period is the amount of time it takes for one event to occur. Period is represented by the letter T, a capital letter T, that's the variable, and it's measured in seconds. So if you would look at the formula that's right there, period is calculated by taking time and dividing by the number of oscillations. So how long it was oscillating and how many oscillations it completed in that time, you can calculate period. And we'll look at some examples of that if it's not clear already. Our next one should be a familiar word, is frequency. So frequency is the number of events over a given time. The frequency is that script F, it's a lowercase script F. I'll write that out when we do work later. It's measured in hertz, which sounds kind of weird. Hertz is just like a physicsy unit named after a physicsy science person. But what it represents is actually 1 divided by seconds, 1 over seconds. That's what a hertz is. And I think that makes a little more sense if you look at the formula. So frequency is equal to the number of oscillations divided by time. Number of oscillations divided by time. Now, I've also got the other formula. You should see that the frequency is just the inverse of the period. It's just flipped. Instead of time divided by oscillations, frequency is oscillations divided by time, or frequency is equal to the inverse of period, and vice versa. We'll look at some examples of that as well. So those are our definitions. That brings us to our very first problem here, number 1, which I will be working out with my handy-dandy whiteboard. So let's take a look at number 1. Number 1 says, a pendulum oscillates 20 times over the course of 10 seconds. What is the frequency and period of the motion? So we have the pendulum oscillates 20 times. We have a number of oscillations that's equal to 20. So 20 oscillations, and it says it takes course. It goes over the course of 10 seconds. So 10 is our delta t, or our time, 10 seconds. So we've got number of oscillations, we've got time. It asks us for frequency, and it asks us for period. So we'll start with frequency, because frequency is listed first. Frequency, script EF, is equal to, if you look back at your notes, is number of oscillations divided by time. So our oscillations is 20. Our time was 10 seconds. 20 divided by 10 is 2. So what you should notice here, 20 has no units, it's just a number of oscillations, and 10 is in seconds. So 1 divided by seconds, 1 over seconds, aka just hertz is what frequency is measured in. All right, so that's frequency. Underline that. The next one is period. Period is capital T. Period. You could remember that frequency is the inverse of period. Period is the inverse of frequency. So you could just find the inverse of this 2 right here. But I'm going to write it out first, and then we'll simplify it later. So if you look back at your notes to the definition we have time, or delta t, divided by number of oscillations. So delta t is 10 seconds. The number of oscillations is 20 oscillations. 10 divided by 20 is 1/2. 1/2, notice 10 is in seconds, 20 has no units, so we're left with seconds. So 1/2, notice that we have 2 for the frequency and 1/2 for a period, so they're just inverses of one another. And that's all we have for number 1. I'll erase this so we can move on to number 2, pause it if you need time. All right, so before we move on to number 2, notice that it's a graph. I actually want to show you a little video clip first of how these graphs are made. These sinusoidal graphs actually they're a really good representation of harmonic motion. But I want to show you a video of how that actually works so you can kind of visualize it. So here's the video. Loading for me. Alright, here's the video. I'm actually going to remove my face so you can see the bottom corner. You don't need to see it. There it is. So the video itself actually connects circular motion to harmonic motion and to graphing, but that's the dot that we're really concerned about, the simple harmonic motion dot. So this one looks like that spring that's moving up and down. In fact, they're about to show, yep, there it is. So there, you see how the dot is following the motion of that spring. So this is simple harmonic motion. And it's going to relate this to a graph in a second. We'll see that sinusoidal graph that we just saw before. Give it a moment. Slow motion. All right, here it comes. There it is. So you see as the dot goes up and down, the x-axis here on the graph is tracking time. So over time, the dot's moving up and down, and so it gives us that sinusoidal shape that you see it's tracing. So now we see how the graphs are made with that sinusoidal shape. It's just as it's moving up and down and back up, it's following that curve of the graph. So I hope that makes a little more sense. Let's go back to number 2 now with the graph on there. So number 2 is it gives you a little graph. It goes up and down, and what it says here is using the graph above, determine the frequency and period of the motion. So the graph got a little picture. It is it starts up high at a high point. So what I think is the easiest way to do this, if we're looking for frequency and period, it's easiest to start with period. So I'll start with the T. Remember that period is the number of oscillations, or sorry, it's time per oscillation rather. The time per number of oscillations. So what I think it's easiest to do to find the period is to find the time it takes to make one oscillation. So if we're making one oscillation, it would be over 1, and then we're just looking for that time that it takes to make one oscillation. So let's take a look at the graph. The graph starts up high, goes down, and back up. So we're looking for one complete oscillation. Oscillation is one back and forth, one full up and down. So if we start up, we go down, then we go back up. So that would be one oscillation. Up, down, back up. So we start up, we go down, and then we go back up, and when we go back up, it's at that 2-second mark. So 2 seconds is how long it takes to make one oscillation. So we put that as our time. 2 seconds per one oscillation, so our period is 2 seconds, aka we have 2 seconds per oscillation, right? It's the time it takes for one oscillation. So that's our period. Frequency, script df, is just equal to the inverse of the period. We've covered that enough. I think I can just do it shorthand. 1 over t. 1 is 1. Our period is 2 seconds. So we see that our frequency is 1/2 1 over seconds, or hertz. So our period was 2. Frequency is 1/2. Pretty straightforward. All right. That brings us to number 3. Number 3. It asks us to, on the axis below, draw a graph with a period of 6 seconds, and it gives you these little axes right here. So I'm going to draw mine on my whiteboard since I don't have a copy of paper right here. On the this y-axis here, we have the y direction, and the x-axis is time in seconds. It's got a couple of hash marks, 2, 4, 6, 8, 10, all the way to 12. All right. So we're looking to draw a period of 6 seconds. If it is a period of 6 seconds, that means it's taking 6 seconds to do one back and forth. I think it's easy here, since we just did one that starts at the top, we'll start at the top again. So we'll start at the top here on the y-axis, and we need to take 6 seconds in order to do one down and back up. So that means if we start up, we need to end up at 6 seconds. So we'll put a dot on the up of 6 seconds. And now, it's a sinusoidal curve. The sines are very smooth. So if you've got one peak here and one peak here, then that bottom right here in the middle should be halfway between, right? So we've got the peak at 0, a peak at 6, which means the bottom should be down here, right in the middle at 3. I like to draw the dots to help me draw the shape a little bit better. So we'll start up here at the top at 0. It goes down, hits the 3 at its bottom, goes back up to the top at 6, and then it continues on like that until it should come back up at 12 on another peak if you're just following through. I think that first 6 seconds is the important part. But yeah, it comes back up to 12. So yeah, that's what your graph should look like. It's got a period of 6 seconds. All right. 4 and 5 are just a repeat of basically the same things as 2 and 3, just again. So if you would, take a moment, pause your video, and try out 4 and 5 on your own, and then come back and watch me check it out. Welcome back. I hope you posted. If not, this sounds weirder. I'm going to erase. I still got 3 on my board, so I will erase and start on 4. All right, number 4. Using the graph above, determine the frequency and period of the motion. So we've got another graph picture, and we're looking for frequency and period. Remember I told you, period's easiest to start with. So we'll start with period. And in order to find the period, we need to find the time it takes for one oscillation. The time it takes for one oscillation is period. So period is t. Let's look at the graph. It starts high at the 20, it starts at the top, goes down again, and back up at the 4 seconds. So we start high at 0, we go down, back up, and we hit our next high point at 4. So obviously we make it takes us 4 seconds to do one oscillation. Period being time divided by oscillations, right? We've done it a couple times now. So 4 seconds divided by 1 is 4 seconds, right? Period, 4 seconds. You could even probably at this point skip that step, right? I think it's fairly easy to look at the graph and be like, one oscillation in 4 seconds, period, 4 seconds. Pretty straightforward. So the frequency, it asks frequency, script EF is equal to the script EF frequency is just 1 over period. So 1 over 4 seconds is 1/4 hertz. And that's our frequency. So yeah, 4 seconds for period, 1/4 for frequency. Lovely. I hope you got it right. On to number 5. All right. On the axis below, draw a graph with a frequency of 0.5 hertz. All right. So this one might have sounded a little tricky to you because the previous one gave you a period and this one gives you a frequency. So that might sound a little confusing, but you can there's 2 steps you could do here, 2 ways rather you could solve this one. So you can either treat this, you can break this down and say, oh, half a hertz is 1 oscillation for 2 seconds, and just look at it that way. Or you can convert it to period, which is what we've been working with. And I kind of do that. You kind of do that in the process of saying what I said before. So I'm going to convert it to period. So if we're looking for period, period t is the inverse of frequency, right? 1 over frequency. So if we have 0.5 hertz as our frequency, remember 0.5 is 1/2. So 1 over 1/2, you're just flipping the 1/2, is 2 seconds for period. So it's 2 seconds for period. I'll draw my axes here. Should have done that before. It's a y and time. All right. So it's got 2, 4, 6, 8. I'm just going to draw up to the 8, and you might see why. So our period is 2 seconds, meaning it takes 2 seconds to do 1 full oscillation. And so we can draw that. You might be tempted again to start high because that's what our 3 other examples are going to do. But for the sake of mixing it up a little bit, I'm going to start low so that it looks a little bit different. So I'm going to start here at the bottom, which means I have to hit another bottom at 2 seconds. 1 full up and down in 2 seconds. So I start here and here. Up and down. Notice that your peak, if you're doing it my way, should be at about 1 second. It should be 1 second, but drawing should be about 1 second. So back up, then back down, and back up, and back down, and back up, and back down, and back up, and so forth, with 2 seconds in between bottoms or tops. So yeah, again, if you started from the top, yours looks a little different than mine, but the idea is that it's 1 full back and forth every 2 seconds. Yeah, I think this one's pretty straightforward. That's the last example we have. You should have a Google Form exit ticket to fill out. I hope you enjoyed. Maybe you need to rewatch. That's fine. That's why I love having the YouTube videos here, because you can rewatch any portion. If you have any questions, just let me know. Google Classroom me, remind, whatever you need.